In this video, I'll talk a little bit about power sets. I'm not going to run through any particular example from the text, but I'd like to motivate the theorem 2.17 in our text, which tells us the number of elements in a power set given the cardinality of the original set. So what I'd like to do here is, remind you of what a power set is. Remember, this is the set of all subsets of another set. So in particular, let's say I have the set A, B, then the power set of A. When I write, I use a curly P rather than the calligraphy P that the book uses. Watch for that. So I ask myself, what are all of the sets that are subsets of A? So 2 always come for free. The empty set is a subset of every set. So no matter what set we're looking at, the empty set is always an element of its power set because it's always a subset of the set itself. What else do we have in here? Well, the set containing A is a subset of A because every element of this set is also an element of that set. We have the set containing B, that's a subset. We also have the set itself. That's the other one that we always have. For any set, we always get that the set itself is a subset of it. Right? For every set A is a subset of itself. So the power set, all the power set does is it takes all of these subsets and it stuffs them in a set. So empty set, set containing A, set containing B, set containing AB. So this is a really natural place, right? We just collect all the subsets of a set. This is a natural place where we see a set of sets, right? So sets of sets aren't just meant to trick students and make them think harder about certain statements. No, they arise naturally. In many situations, it's really natural to think of a set of sets. And so we need to be able to deal with that. This is sort of future motivating the past, that last video, giving another reason for why I ask those tough questions with sets containing other sets. And so, this is how to take a power set. I want to just list out for various cardinalities n and compare that to the cardinality of the power set of that set. And it shouldn't matter what the set is, right? This isn't going to influence how many elements are in the power set. Hopefully that's fairly obvious. But we'll just start, so n equals 0, 1, 2, 3 is probably all I want to do. I don't want to go past that, otherwise I'll be writing too much stuff. And I just want to compare. So let's take a set with no elements in it and figure out what the cardinality of its power set is. So there's only one set with no elements, namely the empty set. And we want to figure out what's the power set of the empty set. So we ask ourselves, what sets are subsets of the empty set? Like I said up here, we always get 2 for free. We get the set itself, and the empty set is always a subset of any set we choose. In this case, the set itself is the empty set, and so this only has one element in it. This is the set containing the empty set. Right? Every element of this set, namely the empty set, is a subset of the original set, the empty set. So the power set of the empty set is the set containing the empty set. In particular, its cardinality is 1. Moving on to n equals 1, well, let's just pick a set with one element in it. How about A is just equal to, the set containing the number 1. Power set of A, we'll ask ourselves, what are all the subsets of the set containing 1? Well, we always get the empty set for free, and we always get the set itself. The set containing 1 is also a subset of the set containing 1. So here there's just 2 subsets. One quick check when you're finding the power set of another set is every element of the power set should itself be a set. So if you find yourself writing it and you write like the number 1 as an element of the power set, you know something's wrong. Every element of the power set should be a set, and moreover, it should be a subset of the original set. That's what the power set is. So how about a set with 2 elements in it? Well, that was like this example up here. A was just the elements A and B, and we had 4 elements in that power set. and then let's say 3, so let's make A equal to A, B, C. Let's find all of the power sets of A. So we always get the empty set. And then one way I like to do this is I like to build my way up. I start with sets containing one element, otherwise known as singletons, and then I'll do the pairs, and then I'll do the triples, and so forth when I'm listing the elements of the power set. So here's the set containing nothing, empty set. We also have the set A, the set B, the set containing C. Then we have the pairs, the set containing A and B, the set containing A and C, and the set containing B and C. Finally, we have the set itself, A. 1, 2, 3, 4, 5, 6, 7, 8 elements in the power set here, and there were 3 elements to begin with. So what's the general pattern here? So if a subset or if a set has cardinality k, the power set will have cardinality 2 to the k. So that's theorem 2.17 states this. We don't have a proof for you in this section. You can think about why that should be true. It's not trivial. It's not that easy to understand why that should be true. We'll talk about it later when we talk about induction, because really induction is sort of the easiest way to prove this statement, and statements like this one. So we will get to that later. We'll see exactly why that's true, but for now you should be able to, given a set, find the power set of it, and be able to tell me the cardinality of that power set, no matter how many elements are in my original set. All right, so that's a bit about power sets. I think that's it.